Welcome back. Let's continue our conversation by now talking about how the freezing point of solutions are different than the freezing point of pure substances. You'll notice that this concept is very similar to what we did with boiling point, with just one little change. So let's look here. When a solution freezes, the solute particles get in the way of the solvent particles freezing. Consequently, the freezing point of a solution is lower than the freezing point of a pure solvent. So as we add more solute to a solvent, we actually decrease the freezing point. It makes it harder for it to freeze. So the equation that we use to represent this is probably going to be very familiar. Delta TF equals KF times molality, where delta TF is the change in freezing point. It's not really the change though, it's more like the decrease. So it's the decrease in the freezing point. KF is a constant. That's also just from that table. And then M, of course, is molality. So this works almost exactly the same as the boiling point equation, except now the big difference here is that when we calculate TF, we have to subtract TF from the initial freezing point in order to get our new freezing point. So very similarly to boiling, when we have a solution and it starts to freeze, the thing that's freezing is the solvent, not the solute. So that means that as we freeze, the concentration of solute increases in the substance that is not frozen. So over time, the concentration of the solution will go up because all of the other parts of the solvent that are freezing, are being removed from the solution. So we can show that in a graph, very similar to a graph that we've done before. We have temperature versus time. And this time, let's start kind of high, because now we are starting at a high energy, and we are going to decrease the amount of energy that's in our substance, and then we freeze it. So this should be what a pure solvent looks like, or a pure substance, whichever one. That's just the solvent by itself. But if we were to look at a graph, and I'm just going to kind of separate them just a little bit like that, just to make sure that we can see the different lines, we would notice that for something that has solute dissolved in it, this is our solution, we would have a lower freezing point and we would have a steady decrease in freezing point as we continue to freeze. And the distance here between these 2 points, this distance here, that's our delta T. So that's why we have to subtract our delta T from our initial freezing point in order to find out our new freezing point. So again, it's the same as boiling point, but we subtract. The actual name for this equation is called freezing point depression. And maybe that helps you remember, because depression means to go down. Boiling point elevation means to go up. So they're kind of inverse of each other. Let's do a little practice. We've already kind of done this practice. So now let's do this practice again. Again, you have the problems written out for you in your notes, and hopefully you did leave a little space for yourself. I'm going to kind of draw lines here, and I'm going to be doing each one of these just to show you how it works. Let's try this first example here. Now we're going to compute the freezing point of 25.5 grams of this nitrotoluene in 100 grams of H2O. So the process works very similar, where we're just going to use this equation this time. So TF equals KF times molality. We already found the molality last time, so we are just going to multiply the KF value, which we're going to flip back into our notes and look on our table. We see that the KF value for water is 1.853. So we're going to use 1.853, and that's multiplied by the molality, which is what we calculated last time. And this time we are going to get a 1.87 degrees. And that's a decrease. That is not an increase this time. So you have to do this in the right order, otherwise it doesn't come out right. So you have to subtract it by the initial freezing point. So freezing point minus TF gives us our new freezing point which is negative 1.87. I figured it out eventually. So try that out. Try it out for the next one. You're going to now calculate the freezing point of 100 grams of naphtha disulfonic acid in 100 grams of H2O. You have the molality already from the last time, so just give it a shot. Come on back when you're done. Same process as before. We use the molality. We multiply it now by Kf instead. We get 6.453. Make sure that you're doing this in the right order because, like I said, the order is really important here. Freezing point minus the Tf gives us the new freezing point, negative 6.43. Let's keep going. We got one more. Let's try this one here. Same process. We are going to be calculating the Tf this time for the freezing point of methyl nitroanthraquinone and nitrobenzene. So go ahead and give it a try. Make sure you look at the table. Remember that nitrobenzene is not water, so you'll need a different Kf value. Come on back when you found the new freezing point. Just like that. Molality times Kf. Remember, we're not dealing with water here, so our Kf is going to be different. That means our freezing point is different, so that's 5.76 minus the change in the freezing point gives us negative 4.8. All right, so remember when we talked about ionic solutions, this works the same thing, or that works the same for freezing point as well. We just have to change our equation a little bit, and the process is the same. So all we're doing is, again, just solving for Tf. We still use the I just like we did before. So if we're looking at this example here like we did last time, it's going to work the exact same way. Our Van't Hoff is the same, so this time we are going to use 2. But now instead of 0.515, we're going to use the Kf value, so that's 1.853. 853. And we are going to multiply that by the molality that we found before. And that gives us a new answer of 5.15. Now if we take that 5.15 and we subtract it, then we get a new freezing point of negative 5.15. I'm pretty sure you probably got this figured out by this point. Now, for number 2, I'm going to let you continue to kind of try and work this one on your own. This time, though, you should find that the freezing point is negative 9.6 degrees. Use that like you did last time. Use it for practice. See if you can figure out and find that answer. Hopefully it works out for you. If not, then let's double check it together. But that's it. Hopefully if you were comfortable with boiling point elevation, you're just as comfortable with freezing point depression. They're painfully similar. So just let me know if you have any questions, but otherwise we'll see you next time.